I can put down strontium layer only, then titanium layer only. So I can make like a really not growing the unit cell by unit cell. It's like a really one packed unit cell, which means strontium oxide layer and titanium oxide layer, you can grow individual layer control. And that allows you to grow strontium titanate epitaxially on silicon, and we'll talk about that next week. And because it's when you grow this on strontium titanate and on silicon, and silicon immediately oxidizes it and forming SiO2 amorphous layer. So in order to overcome this, and they have to use a strontium layer first. If you go titanium go first, then titanium silicide forms, which means titanium silicide is not ideal. So you have to overcome, so what kind of element do you go touch first? And that's the way you have a more degree of freedom you can play. But at the same time, and then you have a lot of flexibility control, but involves cost, involves a lot of learning curve, and then you need a lot of experience and then control this, because it's a lot of human factors as well. And then another method is, as I said, is composite source, which is less controllable, looks like, but it's very easy to adapt and use it. What that means is, for example, your strontium titanate and then yttrium copper oxide, or even 6, 7, 8 elements, you want to do this way. You have for example, you have a 7 elemental compound source. You have 7 elemental composite, like a compound of oxide material, for example. In that case, you need 7 sources. You have to control 7 of them individually, precisely stoichiometry of 1, 1, 1, 1, 1, 1 ratio, or 2, 2, 3, 5 ratio, whatever ratio it is. And that means it's nightmare to control those. Okay? So in order to do easy way to do, okay, that's simple. Just mix everything into one target. And then you making this target just to weigh the actual cations you are going to add. Precisely weigh it and mix it and grind it, make a completely reactive composite. Okay? It's not really composite means of like individual cations, but it's completely reactive and same kind of phase pure actually composite material. For example, you make an yttrium barium copper oxide target. It's not yttrium oxide, barium oxide, copper oxide mixing it. It's a yttrium barium copper oxide, exactly 1 to 3 compound, actually phase, exactly structure, same structure phase, and then you make this bulk material. And this bulk material synthesis is any lab can do. You only have like a mortar, like grinding, you weighing machine, and then you have a ball mill, and you have a furnace and press. That's it. And we have our lab, even though we have a thin film lab, and we have a dedicated actual powder labs to making all the targets. The reason is that the making your own target is commercially available targets limited. And when you call and ask your commercial companies, okay, I want to make this particular new materials I want to try. They've never done it. They don't know how to make it, or they can be very expensive. So easiest way to do is you have a lot of expertise as ceramic people. They can do better, or they can be faster, and then they can have a much more flexibility of control of this composition. So that is the flexibility is a lot of labs can do. And the reason I introduced this, and then you have a 2 extreme of thin film synthesis. One is you cost $2 million of equipment, and with a very precise control of a certain type of experiment. But a lot of experiment, exciting experiment can be done without doing this, and then very simple process, and which you can do as long as you understand the processing parameters, and you can do thin films as good or sometimes even better than MBA grown films. Okay? The reason behind this, I'll explain it. Why this is so advantageous than the other one? Because it's composite target. When you mix this one, already reacted one, then you don't have to worry about oxidation of the source. Source is already oxidized, and source is stable. So then you can put no matter how much oxygen in the vacuum chamber, and then it doesn't matter. But however, when you do this kind of chamber, you cannot put a lot of oxygen in the chamber. As soon as we put a lot of oxygen, and all the sources oxidize. Okay? Once you oxidize the source, then you're forming the oxide layer on the top of this like strontium metals or whatever metal, and your flux very unstable because it's covered by oxide. The atomic flux cannot come out of this oxide layer. So you have a very narrow window you can bring oxygen in, which means sometimes you grow materials and came out in the chamber is very oxygen deficient. For example, you grow like a barium titanium ion beam, and the crystalline quality is almost perfect. For electrical measurement, it's very leaky because a lot of oxygen vacancies. Because when you grow this, the oxygen is not enough, and then it's very leaky. And then this really what you need: high quality of ferroelectric properties, but leaky. You cannot really switch this one. Okay, so that's sometimes some applications, some experiment, some physics experiment may benefit from this type of work. But a lot of other ones, you can use composite target process. As I mentioned here, this approach is very easily adaptable and very useful those. And then there's two main methods applied and used in many groups. First one is pulsed laser deposition, and which is already introduced yesterday, and with a high pressure in situ read. But it's those two techniques, and they use exactly same kind of reactive powder and reactive composite target, and maybe size is a little different, but exactly same material, but it's actually generating flux, generating this flux of like a strontium, titanium, whatever oxygen, or yttrium, barium, copper oxide flux. And you actually use either using photon or using this momentum transfer using argon ions, the mechanical just momentum transfer. So there are two different simple ways to do, but those two are very versatile and easily adaptable. And then one of the disadvantages of pulsed laser deposition in many groups are doing, and then you have an initial cost of this is a laser. Most of people use the excimer laser. Okay, excimer laser most of people use a krypton fluoride, krypton and fluorine. You mix it with neon and then buffer gas, and which is one of the main costs of your system. And then you have optics. You have a lot of optics involved, and also you have adjustment. There's actual a lot of tweaking of the focusing and then beam profiling. You have a lot of issues, and then because of this one involves very uniform energy density on top of the target to remove this gas, the atomic flux, and you need to have a lot of fine tuning of this. So we have my group have both techniques, sputtering and POD. And we have multiple chambers for POD, multiple chambers for the sputtering. But certain materials we use POD, certain materials sputtering, and there's some reason for that. And then, but sputtering here is a lot of advantages, and then that's what I'm going to talk about. We have spent time, and those two, what's the advantage, what's the important parameters, and you can do that. So here I want to ask you guys here, how many of you have done POD in your lab? Okay, how many have done sputtering in your lab? Okay, these are all the oxide material, is that correct? Or just the different materials? Oxide materials. Okay, so I'm going to talk about the POD. You have some experience, and then sputtering has some experience. And then when you actually deposit the thin films, and people report this thin film characteristics, and the way it spends on like a certain section of paper, talk about how they grow, what the quality of this, how they characterize it, and we end up this structure. Then we measure these properties, and we found this interesting phenomena, and what we believe was happening. And that's a simple way of story actually talk about this new materials we actually talk about. And then, when you actually make this material, when you read the papers, it's immediately you can see quantity of thin films from the few sentences or one paragraph. You will know what the quality of material. And that is very important because you are actually the best quality material and giving best science. And the material is not good enough, then whatever you measure is not real intrinsic practice, which means it's not really probing fundamental science what's going on. Maybe some other extrinsic effect is embedded and then masked, and then those intrinsic properties. So I think it's very important to actually make materials and then high quality, but doesn't necessary to you need a very expensive and the highest control system like the MB or anything like that. Okay, so talk about here. So the technique is laser, the PLD, and PLD system is a very simple. You have it here is target materials. Okay, target is composite target, and then size of composite target, as you know, mostly 1 inch diameter, and then you mount it here in the multiple target carousel. So you can have a 1, 2, 3, 4, 5, many targets in single chamber. It's a very compact design, and chamber can be much smaller. And then your laser window bring the krypton fluoride 248 nanometer of exciton laser. That's the most popular and then the laser used. Well, some people use the frequency doubling, tripling, and the YAG laser, and then make an infrared laser to a UV laser, and then to make energy density, the wavelengths get smaller. And then, but I think you can use different source of laser can be used. Sometimes some people use argon fluoride laser, certain material system, but argon fluoride is a little bit dangerous because it generates a lot of ozons. And you have to be very careful in using low 196 of argon fluoride laser. So it's most people and use a krypton fluoride laser, which is a very popular one. And then you have the opposite side, just simple the heater, and then but this chamber is very compact, small, but outside here, where the laser beam comes from, you have to bring the laser first. Then you have to make a beam profiling, very uniform regional beam profile, because your atomic flux and composition, all these things, depending on energy density of the local energy density on the target. So when you do, I wanted the 1 joule per square centimeter energy density, which means the average of every density, but different regions have a different energy density, and because the beam profile in the center is high, but if the edge region, beam profile drops like this. So we don't use all the beam profile, you cut it most apart, and then you use a very flat top region, because the energy profile coming like this, and then you actually throw away most of this part, and use a very, very narrow regions of uniform top region, because that is what you need. And then you beam profile. At the same time, another experience we do is actually most of laser beam comes like this way. Okay, beam is coming this way, and then when you come here, it's coming 45 degrees. Okay, the 45 degree like this, which means you come down to my here. This is my target. This target, and beam coming in 45 degrees like this. Okay, and then think about it. Beam coming here. Then you have to focus this target surface. And then this region is very long, this region. Then this will focus, this region is on the focus. And then you want to focus this region, this one is over focus. Okay? This serious problem of the PLD system. Okay? You don't want to have this under focus and over focus. How do you overcome this problem? Okay? The most laser coming this way. And then what you do, I think this is what the tricks that we have learned from this one. You rotate this beam. Okay, because the laser beam coming is all the XML laser is a rectangular shape beam profile, and then different laser has different one. So you rotate this beam from this one to this. Okay, then your beam is coming this way, and you have a less likely over focus on the focus. You understand that? So it's a lot of very trivial things, thin film growth. A lot of people just ignore just a lot of small details. That makes a big difference in the quality of materials you grow. No matter how you try to do work hard. And then this one growing here, stoichiometry of this one, stoichiometry of this region, you're coming this different composition and different material. And you're trying to make some optimizing this one hard, but you never be able to optimize it because the beam profile is overfocus, under focus, and this region, that region has a different energy density and a different way of coming out. Okay, so this one requires from here to here. If you know the simple optics, 3 meters. You have 3 meters, reflect 3 times, then you go from here to here. You can rotate it. Okay. If you after this class and this lecture, if you want how to do it, I'll tell you how to do that. Just by 3 UV meter, then you just reflect 1, 2, 3. Then you're coming from here to here. So once you rotate it, then you just use this beam, make sure that region, uniform region, cut it by aperture. Then you use a lens to focus this. Okay, that's what the POD uses. So these are small things, and then you have to have a right optics, right distance, and then all these things is involved in this region. And that's why the quality of POD influence varies a lot, and depending on how much you know, how much you control this. And sometimes we actually use beam profile, image the beam profile, and then you have some instrument, and you can actually image the whole thing. Then you know exactly what the energy profile is. I think that tells three-dimensional plot. And then you can cut it in good regions. So POD, I do not want to talk about too much of this because I already talked about it a little bit yesterday. But today I'm going to focus this lecture, first lecture today, is sputtering. The reason that I brought the sputtering here is you can actually use this sputtering any labs here, an existing chamber, and then you just modify it. Anybody can do. Anybody can make a really high quality thin films. Any compound you want to do, very easily can do it. And then that's what I'm going to talk about here today. Okay? And then, but it's a lot of interesting parameters you understand. It's the fundamentals of sputtering is what the issue, why is this is hard initially, and now what is to really make this one is really attractive. So most of the people try many years this oxide thin film growth by sputtering this geometry. Okay? And the sputtering is coming from, look, this is a composite target, and then I just draw here strontium ruthenium oxide target, and you have 2 different cations, and strontium and ruthenium and oxygen yellow one. Okay, so we have a 3 element, 2 cations and one anions. So the way sputtering works is you know that, and then either RF or DC. Then you need DC for conductive material, and RF you need insulating material. But basically you can sputter any material, any limitation, any melting temperature. Tungsten, even you can sputter. Sapphire, you can sputter any materials, no issue of temperature. Okay, so that is the beauty of this sputtering, and then you can actually use this. But you have 2 ways you can think about. You want to do metal composite or ceramic composite. And then ceramic composite is flexible because you don't have to worry about oxidation at all. And so you have this ceramic composite, and some ceramics can be conductive, some ceramics can be insulating. And you can decide what kind of target, what kind of sputtering, depending on your material's conductivity. Okay? So that is some crossover, but I think you can decide what is the optimum one. So you need target is mounted on the sputter gun. Sputter gun is just you can actually buy sputter gun maybe $2,000-3,000, and in the good sputter gun. But you can actually make your own sputter gun if you know how to do that. Just simple inside the anode, water-cooled anode. You have a magnet, and then your ground shield, and that's all. It's very simple. And then, but I think you can easily buy the sputter guns, and use the power supply, apply the voltage here, and negative bias to here, and attract argon ions. Okay? The argon ions are attracted and then bombard, and then your sputter, strontium and ruthenium and oxygen all comes out. But a lot of people initially didn't realize what the serious problem of this sputtering. And the problem is when you sputter, not just this metal, strontium and ruthenium, is either neutral or you have ions. You can have a come out both. Okay? Because so when you sputter, when you break the bond, it can be ions or it can be neutral. And the ions can be easily combined with electrons become the neutral. But look at this oxygen is also come out from the target because the ceramic target contains oxygen. So when your oxygen come out, this oxygen is oxygen minus 2 ions. And this one is a problem because you bias, this one is bias, negative bias. Because when you negative bias, you minus like a few hundred volts. And few hundred volts attract this positive ion to hit it, knock out this. But another this problem is this negative bias accelerate these oxygen ions very high energy. Okay? So you have a few hundred EV, a few hundred EV of this energy accelerating this oxygen ion with the material was already deposited. Okay? You know what happened this one? And this is my experience initially. I grow these thin films and ended up I did nothing. I get nothing, but what I got is just etching of the material, etching of the substrate. Because this energetic particle is much more stronger than depositing of this material. Not only back sputter this, even sputter back sputters front, and then substrate. This is even worse if you sputter fluoride. Okay? The fluoride is F minus. Its ion is very reactive, and then accelerate this one, then etch it very quickly. So you have an issue here, negative ion issue in all oxide deposition. That's why initially many years people try to use the sputtering of this. Okay, sputtering doesn't work. Everybody give up, and then we don't want to do that. And that's a serious problem for many, initially when high TC was discovered. Okay? So you have a multiple approach you can think of, well, overcome this problem. Maybe you can have a very easily, you can think of what's the best approach to do that. And the two approach, we can think about two different approaches. Most of sputter deposition, and what you guys use to sputter deposition, and sputtering has only a few variables. Okay, very simple variables. One, what's the pressure of the partial pressure of the gas in it, and what's the power you apply this, and then power includes what the voltage and what is the actual current on the target, which is automatically adjusted, and then temperature of your deposition. Very simple, that's it. Not much of flexibility of you can control this. And then, so when you do this initially, when you do this, sputtering, you do most of people sputter like the metals, and then a lot of people do sputtering in the range of pressure, roughly 3 millitorr to like a 10 millitorr of that region. You know that the millitorr, I mean, the 1 atmosphere pressure is 760 torr, and then that is roughly 3 to 10 millitorr for the magnetron sputtering, because the magnetron sputtering is a much more effective and higher flux. That's why they developed the magnetron sputtering. But the range of pressure relatively like a 3 to like I said 10 millitorr of that range. Okay, because that is the most effective way and high your growth rate and then things like that. Okay, but those regions you have mean free path is a short but not very short. It's still long. So that means this oxygen coming out scattered by these argon gas molecules, but not strong enough. It reached that here still very high energy particle. Okay, so one approach people use. Okay, simple approach. Why don't you put tons of gas in it? Okay, you put it in like a 400 millitorr. Okay, that's 3 to 400. You're actually putting 100 times more argon gas in the chamber. 100 times, which means 400 millitorr or 600 millitorr, that region, 100 times more, your mean phase is very, very short. Then its oxygen ion scatters so many times. And when you reach here, and you lose most of the energy, and then you don't have such kind of strong molecules, backsputtering. But problem is, so many scattering, not only scatter this one too. So that means you don't get not oxygen, but you don't get this flux. So in order to overcome this problem, they actually distance very short. Usually sputtering, a lot of chambers sputtering distance like this far, some sputtering this far. But make this sputtering smaller, thinner and thinner, is that small, like even 5 centimeter distance. Okay? Very, very close. And that's one way you overcome this problem. But still you have negative ion issue. And then even though you have that high pressure. So another simple approach is, well, let's change the geometry. And geometry is that way. Then you can change the geometry and then remove this problem. Okay, that's the problem. We call this 90-degree offset sputtering. Okay? And then this technique is use a target is 90 degree, and then you apply the pressure is high enough, the pressure high enough, and then you have a lot of scattering. Your scattering is coming from the background gas, and then your diffusion is the main process of the flux. But oxygen ions never reach here. Oxygen ions going that direction. Okay? So this is called 90-degree offset sputtering, and that has been initially this is the first I tried. This is many years of this geometry. Every time I grow this superconducting thin films, it's not superconducting, or it can be like insulating because the stoichiometry is not correct. But the problem of this one is oxygen here. It's not sputter all of them. Sputter, back sputtering of this selectively. Selectively means some elements sputter easily because sputtering yield depending on mass, energy, a lot of things. So for example, this one selectively sputter ruthenium, not strontium. That means you ended up, you provide this flux, the 1-to-1 ratio, but you ended up, actual thin films is not 1-to-1, 1 to 0.5, because you back sputter ruthenium a lot. So you ended up, stoichiometry is wrong, even though your stoichiometry is 1-to-1 ratio, and your stoichiometry is 1 to 0.5. Well, initially, people what did is a very simple way to do. Okay, you lose 50%. Okay, why don't you add 15% more? They use a 2-to-1 ratio target and do it. But this is trial and error. You change the tweaking a little bit, different element. You don't know exactly how composition of target you have to use. This is like a moving target. You're just shooting the moving target. Okay? So that's not a very smart way to do. So you have to do some techniques can allow you to 1-to-1 and you get 1-to-1. And then this technique actually allow you to grow stoichiometric film any oxide compound. And then because certain compound has a more ionic nature. The yttrium barium copper oxide is one of the very ionic, very vulnerable to negative ion. Some oxide less vulnerable and less susceptible to negative ion, but you have a wide range of this negative ion problem. So simple way to do, okay, let's change the geometry and then solve all the problems of stoichiometry issue. As I said in the beginning of this first slide, the stoichiometric control is the one most important thing you have to check when you grow the thin films. If a stoichiometry is wrong, then there's crystalline quality, all the things is no meaningful because your material is not the right material you are growing, and you have to control the stoichiometry exactly what you want. And this one allow you to do that. So sputtering is offset sputtering, very easy to set up and inexpensive. You basically need sputter source and you need a power supply, and then your growth itself is very reproducible. And then anybody can actually come in, and then you have a setup, and then your films, it run to run, is very reproducible. And another easy part you can think about, deposition is very uniform large area. Because of pulsar laser deposition issue here, you pulsar laser beam focus very tiny spot. And then where area you can grow, uniform area, maybe maximum area you can grow is maybe 10 millimeter, 10 millimeter by 10 millimeter, or 1 centimeter, 1 centimeter. Maybe that's the maximum uniformity area. Beyond this, your composition and the thickness profile drop dramatically. So sputtering is advantage here. You have a sputter gun, you can scale up, sputter 2 inches, 3 inches in large size. You can scale up, but uniformity is a lot better, and then you can grow multiple films and the same composition and same condition, and you can grow multiple samples. And the other one is the film quality is very smooth, and initially we got the better films and by sputtering the PLD, because PLD creating a lot of boulders and particles, and then because of this energetic photons, not only just creating atoms, but a lot of chunk of material coming from the target, and especially target density is not good enough, then you get a lot of particles. I think you have some experience, certain material system, you get a lot of particles in the PLD, but sputtering is less susceptible to the particle issue. And the drawback is deposition rate is relatively slow. But a lot of research environment, and then these days, if a slow deposition is advantageous growing highest quality material, because you have enough time to atoms move around and then you crystallize it. And then that's why a lot of MBE growth is growth takes a very long time, very slow. And then sputtering is relatively slow, but I think that's sometimes advantageous of it. Important sputtering parameters, as I said, is only few important parameters. But I think I just want to make this one a list of these parameters, and then gas partial pressure. Basically, you put it in argon gas, sputter gas, and then oxygen reactive gas. And then total pressure range is 50 to 400 millitorr range. But I think this one can be, you can tune, and then once you fix it, and you can have pretty reproducible growth. And geometry fixed, whatever distance here, the distance here, what the distance here, what's the distance here, depending on the size of target and size of here. But you can get easily 2-inch area, you can uniformly deposit in 2-inch diameter area with this. And then here, you have the bias voltage. I mean, this is pretty much determined by this your sputter gun. And then RF case, you have like RF power sputtering, usually run it 100 watts of the power, because you have too much power on your target actually melt. It's too much energy, because even though you cool this, certain targets, ceramic target, thermal conductivity is not as good as the metal, and you don't want to tip too much of the ion energy on the local area. So we have usually run it 100 watts. And then magnetic configuration is mostly like planar magnetron sputtering. So I think it's pretty much fixed when you buy your sputter gun, already fixed. And the sputtering target is diameter, and that actually scale up, and then you can have a substrate temperature. So this temperature is for uniform for all the deposition temperature, deposition techniques. So that means basically what you have to control, number 1 and number 2 and number 4, 5. That's it. Very simple. And then once you set this one, every run is supposed to be very reproducible. And then so let me just introduce this distinct difference between this on-axis sputtering and off-axis sputtering, how much different this case. When you do on-axis sputtering here, and you see that this composition of yttrium, barium, copper, the composition cross the sample here. You know how this one is, uniformity is terrible here, because certain region its uniformity is really bad. And the problem here, uniformity is worse uniformity certain region here, is because your target here is this particle coming from this erosion area is a ring pattern, a ring shape of pattern. And those region has the highest like a negative ion flux. So whenever you hit the highest negative ion region, you get the most serious negative ion bombardment. So you see the non-uniformity is coming from which region has more negative ions. And but not only non-uniformity, it still accumulates a lot of composition. So that's why this much there's a lot of struggle. But using just changing this geometry, your composition is pretty uniform over the area, like a 2-inch area, and the thickness and the composition is very uniform, and then the property is very, very uniform. So I think this is the one thing you can easily use composite targets and take this one, mount it, and use it. So this is a geometry we actually use. Like erosion pattern is usually magnet is the dot, like a button magnet, and outside the ring magnet here, donut magnet. So the erosion pattern is like a dark region here. So then I think we have a negative ion more coming here, and this is the geometry I draw here. So when you look at this geometry, okay, so you want to get small size of sample, like a 10 centimeter or 10 millimeter or 10 millimeter, or like a few samples of 10 millimeter or 10 millimeter samples, and you don't need to do anything, just to grow this influence. But I want to grow uniformity large area. Okay, like I want to grow 3-inch wafers. I want to grow uniform area 3-inch wafers. How can you do by PLD? You grow PLD. One approach people use PLD, and you use like a scanning of the actual target. It takes a lot of time to scan this, cover the whole region, 10-inch by 10-inch by mask covered, and then that's one. But in here, as long as you understand flux profile, what is the profile looks like, and then we just measure the profile. And this is a profile of FX sputtering, a thickness profile. It's not composition profile, a thickness profile. So composition is a lot more forgiving than thickness profile. Okay? So that means composition here is not much different, but thickness drops here a lot. Okay? So in order to overcome, and then this is done like by just the measurement of the matrix. It's like here, you measure the thickness of this wafer of 8-inch wafer area, for example. Okay, we have 8-inch, this whole 8-inch wafer. You deposit this, measure the thickness, and this profile. Okay, so this is a plateau or top region, but drops a lot. Then you can find this rotation. You rotate this, then you can actually average the thickness. Then you can get a large uniform area. So that can be done finding this one exactly where the rotation axis. You can define it by simple simulation, right? You know that the profile, fixed profile, and where is the optimum axis of rotational axis. Okay, that can be done easily by computer programming. And you find, for example, okay, I want a rotational axis here. And this region, this axis is a symmetric, but this axis is symmetric. Okay, so symmetric or symmetric. So this is the erosion pattern of this one, like a 2-inch and the 3-inch target. You have a different thing. So you can actually use a different size of target and then monitor the thickness. And you can see that 2-inch target is much drops faster than this one is a 3-inch target. Okay, so you have a self-bias voltage versus forward power, and then this is what the depending on power and bias voltage, you have the few hundred to 200 volts, which is you cannot really control. It's actually is determined by your calculation. But you can see that the 3-inch target, your profile is better than 2-inch target, but not as dramatically different. Okay, but obviously this one is a percentage thickness, but actual rate is faster because your flux from the 3-inch target is higher. So advantage of larger diameter target is higher flux and also better uniformity without rotation. But you can actually do additional advantage of this other direction. You can see that this way and that way, you can have two different axes. This one is axis scanned along that direction. And then this direction is y direction is that one, and x direction is that one. So you can average this. Once you average this and rotating substrate, you get this kind of profile, and without rotation, profile drops like this. So that means you can have a relatively uniform deposition, and then this is like a plus minus 10% or plus minus 5% average. You can actually define it. What is the range of the uniformity? You can design actually this rotational axis. Okay, that is you can sometimes the reason initially is the large area uniformity is important. I want to grow microwave device or superconductor microwave device on 1-inch wafer, 2-inch wafers, because you want to make like a streamline resonators, a lot of those things. You need the wafer this size, wafer to get. And sometimes I want to do process in a piezo device, okay, one of the piezo MEMS, for example, and I need to use large wafers, not the small size wafers, because that allow you to do by silicon integration, oxide on silicon. The silicon wafer comes with a 2, 3, 4, 5, 6, 8-inch wafers. So this one can be scaled up, and this one actually demonstrates up to 8-inch. Actually 3-inch diameter target, you can get 8-inch wafer area uniformly covered within plus minus whatever 5-10% region. Okay, so that is a very attractive. And then other techniques is much harder to adapt to this, but this one is simply you have a simple rotation, aspiring target, and then those things. And there's a composition of this composition measurement and composition yttrium-bearing copper oxide relatively uniform here. And then a lot of composition as we do is a wavelength dispersed X-ray spectroscopy measurement, and the error bar is actually is relatively small, and then that's what you get. Okay, so this is actually superconducting transient temperature. You can see how sharp the transition, and the sputter yttrium-bearing copper thin films. And you can see that 91 Kelvin, it's a very high GC temperature, and that this is as good as one of the best thin films you can grow. And how sharp the transition, you can see that from here to here, a very sharp transition. And then you can normal state resistivity is quite good. And then this is typical, you can get the optics sputtering. You can use this technique for all other materials. And then this I encourage you to actually try if you want to try something new material system. Very easy to do. Okay, I'm going to skip this one because I'm going to go about 1 hour now. But, okay, one of the advantages of sputtering is versatile, uniform area, and reproducible very easy. But, can you do same kind of in situ monitoring for the sputtering? No one has done that yet. The pulsar laser deposition, I showed that high pressure read and control atomic layer control. And the sputtering, people never tried this. And then one of the people, reason why they didn't try it is a read, is you have a magnet. Sputter gun has a magnet. You have a magnet inside, in the chamber, then you bend the electron beams. You bend the electron beam, then your actual read does not effectively work as the PLD. Because when you do PLD in the read, you have to do a lot of shielding. There's some kind of the new metal shielding, so you have to avoid some magnetic field. And then so the digital control by sputtering is a lot of advantage. And then interesting oxide, you can grow yttrium-bearing copper, strontium luteinate, and one of the best, like a superlattices, by grown John Mark Triscon's group and University of Geneva. And this was a lanthanum nickelate, lanthanum manganate. There's a 111 orientation has exchange bias, but 100 doesn't have exchange bias. This is published in Nature Materials in 2012. They use this material sputtering by superlattices. And very high quality superlattice, you can see that it's superlattice reflections and a very uniform smooth, like atomically flat surfaces and grown by sputtering. But they didn't use in situ monitoring. They just measure actually your rate, grow thick film, they measure the rate, divide the time, then you know what the rate per second. And then you just multiply this time to grow whatever you need cell to grow. For example, they want to grow I want to grow 5 unit cell and 5 unit cell, then you actually use a time to control those things. But they get the beautiful data by sputtering, and then you have a beautiful physics and beautiful science they put on by sputtering. Okay, not many groups are doing it at this point, but I think this potential is very useful and a very strong the capability. And then sputtering is different from POD and MBE, and then combined with sputtering to access a new material space is another advantage. Okay, so can you do this one? Yes, we can do that. But the design here is a normal design, is the phosphorus screen, and then your sputter gun here, okay, and the heater, the off-leg sputter, like this is a sputter. The target is here, and this is the heater block, and E-gun coming in, and then you can see the read pattern, oscillation. Then this one can be oscillate, tilting, and azimuthal, and you can control the read pattern. And the challenge here, as I said, magnetic field. Okay, the magnetic field is coming from the sputter gun, and the sputter gun magnetic field can bend the electron field. Second problem is your background gas here is a lot of argon. Argon has a heavier than oxygen, so your scattering by argon is more severe than oxygen, and then that's another one. So we look at this magnetic field pattern here. This is a console simulation, and you can do a lot of electromagnetic the simulation, and the sputter magnet, and then creating a lot of magnetic field, and then that actually, because this, without magnetic field, your spot is very symmetric here. But when you bring magnetic field, you have bending the magnet is like this. Okay, so not very symmetric. So that means still we can actually use this information to actually monitor the growth, but not perfectly ideal. And then there's a vacuum, and then you have magnetic field is bending this one. So I think it's not, you still can do monitor this oscillation of this, we can do it, but you can see that from this pattern you can tell, but you want to make this one more flat and a nice peg. And then, so you can actually see that with oxygen and argon, the oxygen scattering is much less than argon. Okay, because you can just clear even same pressure of the gas oxygen, 75 millitorr, and they're very bright, but argon scatter a lot more. So the more stringent requirement to grow this material system. Okay, so now this argon scattering cross section right here 4 times larger than oxygen, and then you have playing the vacuum and 200 millitorr, you get high pressure, and then you get a lot of like diffuse scattering. So what you did here initially, okay, even you have this kind of issue, and then your on-axis and off-axis you try both ways, and you can still see that this oscillation, not as clear as a POD, but you can actually do this, and then even off-axis sputtering, you get a lot of oscillation here, but this noise level is higher because background pressure is high. But still we can actually see very similar type of work, like a POD and the sputtering, and then you can adapt to this one for this deposition, and then this try this different material like a lanthanum strontium manganate. You can see that this pattern is bending like this, and you have the oscillation is very clear. So depending on materials, you can see the very clear oscillation, layer by layer growth, and lanthanum strontium manganate, which means you can use very simple technique like a PLD, but your sputtering can do a lot more degree of freedom, uniformity, and different materials. Even you can use in situ monitoring by sputtering, and then so we can have really control atomic layer controlled growth, and by off-axis sputtering. And these are the PLD grown LSMO and the sputter grown LSMO, and you can see the pattern here, a bit of a bend here, but you can eventually see the same thing. Okay, so this one, so we have a strontium lutherate, and then we actually see very similar. I'll talk about this later because I haven't covered this one yet. But you can transition from layer by layer growth to step flow growth, and you have seen this, and you have seen the same thing in strontium luthenate, and we can see the same thing here. But in the strontium luthenate in sputter case, we do not see the step flow growth all the way. We go to the two-dimensional growth because of step growth, and there is two different techniques and a different regime of the parameter space. And one goes step flow, one goes two-dimensional ion growth. But actually, you can study growth mode and the layer by layer control, and you can do uniform deposition large area, and most importantly, you can grow stoichiometric thin films. Okay. So I think this surface roughness, and then you have a thickness oscillation of sputter film with as good as the POD. But one thing we actually use this computer simulation of the console allow you to design your chamber to minimize your magnetic field actually pattern. So use the simulate magnetic field pattern, and then when you do that using single target, like this off-fix sputtering, using one target. If you one target, E-gun actually electric field bent this much. So that means you miss the screen. Okay? So this, then you have a geometry, you don't know exactly where you put it in. When you have this bending of this, you have a off-fix sputtering, bending that way, in the plane, bending this direction, so miss this way. I think this is a top view or the side view. Okay? Can you see that? This sputter gun, off-fix sputter gun, and there's a heater, the substrate sitting here, electron gun, going like this, like this, like this. See that? Go like this. So that means your screen is sitting here, you go bend like this, then you have to put this one up here. If you overcome to do that, you have to use simulation to solve this problem, and then using compensating the magnetic field using another gun the other side. That's a simple way to do it. Okay? Can you compensate it? So about two guns. Okay? Your two guns is an advantage. Two guns. You have two materials. Maybe superlattice you want to grow one material, other material, and the two of those. And then you have even though you don't use the second guns, then compensate the magnetic field, and then allow two guns are needed for superlattices and multi-layers. But you can see that these two guns is even worse than single gun, but depending on your polarity of magnets. Because when you do your magnet, you have an intercenter magnet and a ring magnet, and then you have N pole, and then outside is S pole, the magnetic field come out like this. But you have other guns, you can do either same polarity or reverse polarity, and then make a plasma configuration different, but at the same time your magnetic field pattern is different. So we can compensate this. So the easy way to do is to compensating this, so it's like an anti-symmetric magnetic gun or symmetric magnetic gun. So you have a changing this anti-symmetric gun, you can see straight beam. This is a very simple thing. You don't have to think about the complicated one. Okay, just changing this polarity. Can you see this one and that one? Okay, so this blue and red. Can you see that one? Anti-symmetric. But the previous one is red and red. That means your polarity is a symmetric gun. Make this kind of even worse than single gun. But you can use a two-gun geometry, make a straight beam. So now you have even more attractive than without reed gun. Sputtering is so attractive, you can actually use not only growing high quality oxide thin films, but you can grow superlattice multi-layers, real in situ, real-time monitoring of this technique using very simple. So when you buy your sputter gun, make sure your two sputter guns anti-symmetric magnetic field. And then if that's the case, and then your beam is go straight. and you can actually see that being straight, and this was the simulation of this. So you can actually have a nice repattern of this. So we built this chamber in our lab, and then use 2 sputter guns with the reed guns, and then so when you set it up, it's right on our fast screen. You hit it. Initially we couldn't see it. Now after do it, the beam is center of the phosphorus screen. So I think this is not very difficult. You can actually adapt this one, and then you can use and then grow high pressure, and then in situ read and multi layers. You can do that, and very nice technique of this. And the symmetric is a comparison of this is a very serious bending problem. Okay, so now I think we have 2 sputter guns face to face, and then in that case, with the advantage of 2 sputter guns, you can use 2 different materials and different material systems. For example, I can use this one is a lanthanum nickelate, or you can use a lanthanum manganate. So that's what John Mark Criscon's group published a paper in Nature Materials, and you have 2 different materials superlattices. But you can use 2 materials, same materials, deposited without rotation. You get more uniformity and thin film massage area. So you can have a flexibility of making single material or multiple material you can do, and that's something you can really consider that. And then you can design your chamber more clever way. Then you can do more than 2. You can do multiple targets you can do, and then constant simulation we did. So our new chamber has multiple actually targets rather than 2, so you can deposit many of those. And another advantage of this system, and then not only read, and then your chamber is relatively compact. And sputter gun is getting very compact, like 2-inch target is that much, and you can have everything in the small area. So I'm going to stop it here, and then I take some questions and a break and come back. And the next subject is something like very more specific, and I can give you some example of your stoichiometric control, like extreme stoichiometric control, what that means. Stoichiometric control, I didn't talk about 0.01% or better, and how many point defects you're talking about. And the next one, I think we talk about, that's the second one, like yesterday we did. I can give you one example, specific example, address stoichiometric issue, and then we can learn more second lecture. Okay. So I can take some questions about this, but I think I can spend 1 hour. I cannot cover all the techniques. I better cover is techniques. It's a very attractive technique you can use, and then easy adaptable. You can use that in the lab. Okay. Any questions? I think that's pretty much of it. Yeah, 4 guns. We can multiple guns. Yeah, you can do design of this. Anyway. Yes.
I'm Sandeep.
Yes.
So, sir, my question is for the off-axis sputtering, how does the film uniformity and stoichiometry depend on the distance between your target and the substrate?
Okay. So, roughly the distance, you can optimize the distance, but usually you can actually see sweet spot. It's a distance. Basically you have avoid direct beam of negative ion. So when you have this off-axis sputter gun this way, if you go too far down, okay, there's a 2 degree of freedom, this distance or this distance, okay? So this distance far down, then your diffusion takes longer, your rate slow down, but you're less likely hit negative ion spread. The negative ion not coming just straight beam, negative ion coming this way, because a lot of flux is a sine cosine law. Okay, cosine law is all the flux. So the cos is coming like this. Okay, so it's coming like this. So that means you're very close to the middle bottom. You can move very close. But if you're far, then you still your negative ion, because negative ion coming this way. You understand that? The cosine law. So you have to really optimize this, but it's not actually very sensitive to do that. So you want to have a distance maybe this one half-centimeter, half-inch distance, and then this distance, you don't know underneath here. You have to go that way. And you go this, not too far, because you go too far, you hit by this negative ion, and also your rate is slow because of your far distance.
So increasing the voltage or power will take care of the deposition rate.
Yes, because in sputtering case, deposition rate is not power. Deposition rate is current density. So in DC, in the DC sputtering, you can read the three different modes: your voltage, power, and current. And the current is the way you determine the actual rate, because your current density is the one. And then normally you see that bias voltage is roughly range of 50 volts to 300 volts, that range. And then if you have a too high voltage, your energetic radical is more likely higher. So it's better to have a low self-bias voltage that's more attractive. But if you go low bias voltage, you get more current because the power divided by the bias voltage. That's current density. So you get scale. Your scales when you go higher voltage and higher power and higher current density. But you cannot go too far because you actually melt your target. Because if not melt the target whole area, a lot of problems happens locally. You heat it up too high because your ceramic target thermal conductivity is very poor. Good question. Yes. Yes.
Sir, in off-axis sputtering, collision cross-section plays a role or not?
Say again. Cross-section of
collision cross-section of different atoms. It does play a role in deciding the stoichiometry of the thin film or not?
Distortion of
Stoichiometry of the thin film which we are depositing.
A stoichiometry.
Yeah.
Your stoichiometry of thin film
Yeah.
compared to PLD, or
actually the different atoms which are coming out of the substrate. The
Okay.
collision cross-section with argon ions. Does it matter?
yeah, that doesn't matter. The sputtering is the process. You have to think about this. Sputtering is initial target. Okay, we have an initial fresh target. Sputtering yield of different elements are different. Okay, for example, you look at the chart, you're depending on mass or different element, and the sputtering yield is the energy. You can find all these things. But sputtering initially is all the elements sputter differently. But once you reach the steady state, surface actually sputter. Surface composition may not be the exactly bulk composition and reach the steady state. And then that steady state maintained. And then flux is maintained with constant same stoichiometry. So very careful is that when you do sputtering, don't sputter right away. You have to pre-sputter and then make steady state condition. So is ideally you bind your target, you pre-sputter for a while, make a conditioning, but each time when you actually grow things, maybe pre-sputter a little bit using the shutter. Then once you reach that steady state, you can actually see that from monitoring your bias voltage. And once you reach that, open your shutter and start depositing. That's the most ideal way to do it.
So one more thing, if I am already having excess oxygen in my substrate, can I reduce the oxygen by some reduction process during deposition using the PLD?
You have already oxygen in the substrate.
Yeah.
Strontium titanium substrate has oxygen.
Yeah, suppose I have SiTiO4 and I want SiTiO3 thin films using PLD. Can I do reduction in the chamber itself in some way to decrease the oxygen content?
Or decrease the oxygen content
Yeah.
of your thin film during the deposition. Okay, so you want to have oxygen content less than
Yes.
your bulk
Yeah.
bulk material. Okay, so you have depending on your compound, allow you to do that. Certain compound is oxygen stoichiometry varied a lot, depending on how much you put it in. For example, some kind of cobaltate. There are a lot of papers about cobaltate, like lanthanum, barium cobaltate, lanthanum cobaltate. Your oxygen stoichiometry can change the different phases in between, and then you can do that. For certain compound, you have only line compound. you cannot change the stoichiometry. Like aluminum oxide, very hard to change aluminum oxide to aluminum oxide minus something, but they're very stable. And then that depending on your material. I don't know your material has how much freedom to do that. And if you have a material that has freedom to do that, you control the oxygen partial pressure, and then you can have a range of oxygen stoichiometry. But you have additional degree of freedom to control the stoichiometry post-annealing. After you deposit at high temperature, you cool down that pressure, you vent oxygen, and then anneal at high temperature, cool down. So you have a post-annealing as another degree of freedom. You can actually use the control of the stoichiometry oxygen. Is that the question?
Partially it answered.
Maybe you can talk about the tea time. Okay. Any more questions about this sputtering? Yes?
Films grown by sputtering and those PLD, does it change some characteristic property of superconducting material in terms of critical current density and some other HC2, etc.?
No. Actually, it's more depending on who grows the thin film probably. But I think initially when you look at the sputter films, has a different characteristics of the PLD initially. But we thought this one is different techniques. But the later is when you optimize the conditions, and as you can see that TC is very similar to PLD grown thin films. And then for PLD grown thin film, you have to be very careful. Like a lot of particles is cuprate materials. When you do cuprate material PLD, you see a lot of boulders because you cuprate is sometimes like a chunk of material come out from the target. But sputtering less susceptible to do that because it's more like an atomic flux rather than cluster definition. And PLD is like sometimes the cluster come out rather than atoms.
Sometimes what happens just for creating more vacancies and kind of things, grain boundaries, etc. The JC varies in general. Like
The JCs.
Yeah, so probably it could affect JC, not at least HC2, but may possible JC may vary because of more defects and some kind of.
You mean the ex situ thin film or in situ thin films?
Honestly, if films are grown differently, like due to variation in some kind of defects and like some extra defects and vacancies, it may create some variation in JC.
Okay, so critical current density has a lot of not just a composition issue.
Mm-hmm.
You measure the critical current density superconductor. I think we can talk about that later too. But it's a physical properties. It's not only depending on composition, especially critical current density. Critical current density is depending on your microstructure, but also flux pinnings. Okay, you have some kind of defects, advantages for flux pinning. So that means you have the gross material perfect, like no defects, like a boxing or crystal. Then critical density is so low because no flux pinning centers. And then, but the thin films, if you grow low temperature, you get a lot of twin boundaries or some kind of other dislocations and all these defects, and critical density a lot higher. So what is the better samples? High critical density sample better or low critical density perfect single crystal better? And answer is both are important, depending on what is the use of your material to study this. I want to demonstrate this YBC or the superconducting thin film samples for the application of like a high magnetic field application and flux pinning and then all these kind of thing, then which is thin film is better. But you want to do something very, very clean and defect, low density defect, certain kind of intrinsic characteristics, maybe boxing crystal is better. But each very hard boxing crystal, very hard to oxidize, very long distance. So sputter films, and initially when you initially reported, critical density came out 10 to the 7 amps per square centimeter, a few times 10 to the 7 amps per square centimeter at 4.2 Kelvin. It's so high. We're surprised why it's so high, but maybe some lot of flux pinning because the films grown at low temperature rather than very, very high temperature. And also other ones, the grain boundaries and how clean the grain boundaries, and that also determine that. Any more questions? Okay, so then we can take a break and then come back and then on another subject, which is point defect, and also I want to introduce very interesting cruise technique, and then maybe that's something future the project. All right? Thank you.